Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. We're in Chapter 25 in a student's guide through the great physics texts. This chapter is titled Induction of Electric Currents. What I'm going to do is start by reading the introduction, the introductory notes about Michael Faraday, and then we'll begin looking at his experimental researches on electricity. So Michael Faraday was born in 1791 in Newington Butts, which is now part of London. It must have been a suburb back then. He had little formal education beyond day school as a young boy. Yet from a position as apprentice to a bookbinder at the age of 14, Faraday would become the superintendent and director of the famous laboratory at the Royal Institution in England, where his careful experimental work on electromagnetism laid the foundation for Maxwell's electromagnetic theory of light. So James Clerk Maxwell, by the way, was a very famous mathematician and scientist right around the time of Faraday. And what Maxwell would do would be to take Faraday's careful experimental results and formulate them into a mathematically self-consistent theory of light. Faraday's scientific career began in 1813 after he presented Sir Humphrey Davy, another famous scientist, with a carefully prepared transcript of notes which he had taken after attending Davy's chemistry lectures in 1812. So in other words, young Faraday, who was working as a bookbinder's apprentice, went to some scientific lectures, took very careful notes, and handed the notes to Sir Humphrey Davy, who had been giving the lectures. Davy was so impressed that he hired him. So Davy asked Faraday to fill a position as his laboratory assistant at the Royal Institution, which Faraday did. Shortly thereafter, he was invited to serve as Davy's secretary on a tour of Europe, where he met and talked with many leading scientific figures, including Ampere in Paris, we've read Ampere in this course, and Volta in Milan, after whom the volt is measured. Returning to England, Faraday's laboratory work initially focused on chemistry and electrolysis. We talked about electrolysis a bit. It's a splitting of water using electricity into hydrogen and oxygen. And Faraday invented many of the terms that are now used in electrochemistry, such as electrolyte, electrode, anode, and cathode. Faraday liquefied chlorine for the first time in 1823, and 2 years later, he isolated and identified the organic compound benzene, which he called bicarburet of hydrogen. Faraday was elected a Fellow of the Royal Society in 1824, a great honor, and in 1826 he initiated a series of Christmas lectures for children, which have been held at the Royal Institution ever since. By the way, if you can get your hands on a book called The Chemical History of a Candle, which is based on Faraday's Christmas lectures, it's a fascinating little book. And he also wrote another book called The Forces of Matter, I believe that's what it's called, by Faraday, which are his Christmas lectures. And these were really designed for young people who would come to presumably the Royal Institution, and he would give demonstrations, which sound like what they would have been fascinating to attend. In any case, picking up again at the bottom of page 299, inspired by the work of Ørsted, Ampere, and Arago, Faraday's attention turned increasingly to electrical and magnetic phenomena. A comprehensive description of his work may be found in a series of articles which was published in the Philosophical Transactions of the Royal Society of London, under the title Experimental Researches in Electricity. Among the seminal discoveries included herein are the rotation of polarized light by an electromagnet, that's now called Faraday rotation, which we talked about a moment ago, and the phenomenon of diamagnetism. By the way, diamagnetism is when you bring a material very close to a magnet and it is repelled by that magnet, even though that object is not normally a magnetic material. But Faraday's most significant discovery, and the topic of the reading selection that we're going to be discussing now, was presented initially in his address to the Royal Society on November 24, 1831. In this lecture, he describes his attempts to obtain electricity from ordinary magnetism. This lecture begins with a brief reminder of how bodies held in electrical tension, we would say they have an electrical potential or voltage difference between them, induce an electrical polarization in nearby materials. Before proceeding, he then explains how his work was inspired, at least in part, by Arago's recently observed magnetic phenomena and by Ampere's beautiful theory of magnets. So that's a short introduction to Faraday's experimental researches in electricity. So let's jump right into it. You see here on page 301 a series of numbers with paragraphs after them. One of the nice things about reading Faraday's work is he was extremely well organized, so you can refer to his papers and a particular paragraph or experiment by number. And He was very organized in the laboratory. Another thing you'll notice about his work is there's little or no mathematics. Certainly there are some numbers, but no mathematical formulas. That's because Faraday himself was not comfortable with mathematics by his own admission. But he was an extremely adept experimenter. He did careful experiments, and I think that will come through in reading these lectures, or these notebooks. He says, for example, that he's going to set up an experiment in some way. He does an experiment, he reports his results, he gives his interpretation, and then he tells how he decided to modify that and how to do another experiment and so on. So it's really a model of how a laboratory notebook should work. Okay, so let's look first at his paragraph number 1. He begins by talking about electric tension. He says the power which electricity of tension possesses of causing an opposite electrical state in its vicinity has been expressed by the general term induction. So you might remember we talked about the induction of polarization. So if we take a positively charged object, like a sphere of metal that's positively charged, and we bring it near some insulating material such as glass, what happens is that glass becomes polarized. So if that metal sphere is positively charged, the negative charges in the glass move over toward that positively charged sphere, and the positive charges in the glass move to the other side. In other words, the glass becomes polarized, and that has been called induction. Now what Faraday is going to do is use the word induction, but in a broader context. He's going to say, he says, as it has been received into scientific language, this term may also, with propriety or appropriately, be used in the same general sense to express the power which electrical currents may possess of inducing any particular state upon matter in their immediate neighborhood, otherwise indifferent. So just as electrical charges can induce an effect in nearby materials, so too he's going to say, can electrical currents induce effects in materials that are nearby? So this is the general sense in which he's going to use the term induction. Okay, and then in the second paragraph, I'm not going to go through this in detail, but he mentions that there have been hints about this in recent work by Ampere and Arago, where they passed electrical currents through wires and found that the material nearby seemed to acquire certain properties, or it had effects on the materials nearby. Okay? And then he goes on to say, in the third paragraph, he's reminding us of Ampere's beautiful theory of magnetism. Remember what Ampere thought was that when you pick up a bar magnet and it pushes on another bar magnet, that can be really understood if you imagine the bar magnet as being comprised of a loop, a stack of current loops, kind of like a helix. Because we know that electrical currents flowing through a helical coil produce magnetic action near that coil. So if I were to draw a picture over here on my sketchbook, if we had a coil of wire like this, and we passed an electrical current through it like this, that is equivalent in some sense to a bar magnet. In other words, the effect on a compass needle near this would be the same as a bar magnet with a north face up here and a south face at the bottom. In other words, the bar magnet would produce, if you put a compass needle near it, it would point in these directions if you put it near it. And likewise, if you take a loop of current, it would also produce the same kind of orientation in compass needles that you place near it. So he's reminding us of this equivalence that Ampere had pointed out. Okay, and then Faraday goes on to say, these considerations, with their consequence, the hope of obtaining electricity from ordinary magnetism, have stimulated me at various times to investigate experimentally the inductive effect of electric currents. So in other words, if electrical currents can produce these magnetic effects nearby, is it possible that it works the other way? In other words, can magnets produce electrical effects? He says, I lately arrived at positive results, and not only had my hopes fulfilled, but obtained a key which appeared to me to open out a full explanation of Arago's magnetic phenomena. And he'll say more about this in a little while. And also to discover a new state which may probably have great influence in some of the most important effects of electric currents. Okay, so he's saying he made a new discovery, and he's going to be talking about this new discovery in the next few pages. He says, these results I purpose describing, not as they were obtained, but in such a manner as to give the most concise view of the whole. So he's not necessarily going to be chronologically reporting what he did in the lab, but presenting them in a way that's logically coherent. Okay, and so that brings us to page 302, and now he's going to describe in detail his experimental technique and what he observed.